Hello, this is Mr. Pruitt, and today I'm going to be talking about basic gravity concepts. And we're going to especially be looking at a closer look at Newton's model of gravity, which was called the law of universal gravitation. So as a review, remember that Newton proposed the law of universal gravitation in his natural philosophy of the principles of mathematics. His law was based on the assumption that gravity was based on the mass of the objects and the distance between them. It was a very good model. It is still used today to calculate gravitational forces, and can be modified to find the strength of the gravitational field of an object. Remember that Einstein used this model, took this idea and proposed a model that could not only calculate gravity, but it also explained why gravity exists by looking at by looking at the curvature of space-time and gravity's effect on it. So when we start to look at this model, the first thing we need to look at is we need to make sure that everybody understands what inversely proportional relationships and directly proportional relationships look like. Directly proportional relationships or direct relationships mean that both variables move in the same direction. Basically, it means that if one thing increases, the thing on the other side of the equal sign also increases. So in this case, the force of gravity would increase by the same amount that the product of the masses would increase. So if you double mass 1 and leave mass 2 the same, then the force of gravity is going to double as well. And the same would be true if you were to double the force of gravity, then one of the masses must be doubling. In an inverse relationship, the variables move opposite one another. So if you increase one, then there has to be a decrease in the other. So in this example, if you were to increase the radius, then the force of gravity would be cut in half. Or if you were to cut the radius in half, then the force of gravity would be doubled, or actually quadrupled, because this is an inverse square relationship. So if I double this one, then it's going to cut this by down to a quarter of what it was, and if I cut this in half, then I'm going to get 4 times the gravitational force. So law of universal gravitation begins with the third law. Remember, the third law says that opposite force pairs must be equal. Both objects, regardless of mass, must be exerting the same amount of gravitational force on each other. So my green smiley face is much larger than my yellow one. They're both attracted to each other, and they both have the same amount of attraction to each other. All right. That means that every planet or comet or asteroid or the sun must exert the same amount of force on the sun as the sun exerts on it. So when Newton's model, whenever we look at the radius measurement is actually from the center of mass of the object. So it would be like this one here on the top, and that's the correct measurement. It goes from the center of mass of the first object to the center of mass of the second object. It would not be correct to measure from the outer edge or the surface of the planet, because on a significantly large object like say Earth, the distance to the center of mass might still be another 4,000 miles or something. The radius portion of Newton's model, remember, is an inverse square relationship. This means that changes in the separation distance affect the gravitational force to a much larger amount than changes in the mass of the object do. So if you look over here, if we have two objects of equal mass and the unit is one, the distance unit is 1 between them, then we get a regular force of gravity. But if we are to double if we took those two equal mass objects and we doubled the distance in it, the gravitational attraction would only be 1/4 of what it was. Or if we were to take those two objects and move them closer together, half the distance, then we would get 4 times the amount of gravitational force. The mass of the object is directly related to the gravitational force. It's directly proportional. So it just means that a change in mass will affect the gravitational force to the exact same proportion. So If I double the mass of one of the objects, I get double the force. If I double the mass of both objects, I get 4 times the force. All right. In Newton's model, we have a constant that we call big G. It's the gravitational constant or the universal gravitational constant. What it is it's the constant of proportionality that makes it necessary. It's necessary to make these calculations in gravity with gravity. Big G is equal to 6.67 times 10 to the negative 11th, and it was first measured in the Cavendish experiment, as shown over here to the right. So, how does gravitational force affect the acceleration between two objects? Well, let's think about this. Let's say that we have two asteroids and they're approaching each other. And so the distance or the radius between their centers of mass is getting smaller and smaller. Since each asteroid is exerting an attractive gravitational force on the other, and it's an equal amount of force, as they approach each other, that distance becomes smaller and smaller and smaller, and so the forces between the gravitational force that each one is experiencing is getting larger. With a larger gravitational force, we're going to get an increase in acceleration or a larger acceleration.